It didn't feel like what.
It also had a check.
What do you want me to achieve by doing that? Just to see if you can see the screen, but one needs to let me into the meeting. Let me in.
Yeah.
Around. So, I think we got 4 presentations. The staff did his in a different session. 5 we've got around. So we've got 10 minutes. I'm going to be tight with that time. So if we go over, then we'll stop here, I'm afraid. But hopefully, we won't come to that. So without further ado, Aitor.
Thank you. Okay, good afternoon. So, well, I will go. I'm Aitor Erkoreka from the University of the Basque Country, and we have been working many years in the different annexes on this average method that has a very interesting approach for the uncertainty estimation of the HTC, because it's the most simple white box that you can use. Yeah, actually, just stay in a building, assuming that the envelope is the control volume, and assuming homogeneous indoor temperature, homogeneous outdoor temperature, and let's say, I know it's not constant infiltration and ventilation heat loss coefficient, but assuming the UA value is also constant, you can make an energy balance. And making the energy balance is a really interesting thing, because instantaneously, when you will see that making the physical model will permit you to relate each of the energy balance term, the accumulation term, the heat losses through the envelope as solar gains, occupancy gain, and heat transfer losses. The work is the electricity consumption that will convert it entirely into heat within the building. And then you might have mass flow rate inlets and exits as ventilation, or imagine that we have a heating system that is fed by water with its entry temperature and leading temperature. If we reorder all that, we actually get this very quite simple equation. It's an instantaneous equation in kilowatts, where we can merge the UA value and the infiltration ventilation heat loss coefficient into the heat transfer coefficient, and we get this very simple equation. This is, if in a certain instant, the solar gains plus the heating gains plus the electrical gains plus the occupancy gains minus the heat loss coefficient or heat transfer coefficient by indoor and by outdoor, it's not 0. That means that we have a variation of the internal energy of the building. Actually, it's very nice, because you relate whatever you want to estimate with measurable variables. Indoor temperature is measurable, outdoor temperature is measurable, heating gains are measurable, electrical gains are measurable, occupancy gains are not measurable, but you can estimate them quite well if you know how many people and their activity level, but this then you will never measure it. You can never measure the instantaneously how much energy is being stored within a building by sensors. This value is impossible to be measured. So when you have one equation and 2 unknowns, we remember, since we were very small kids, that it's impossible to solve it, because you will never get a good estimate of the heat loss coefficient if you cannot measure this. So the mathematics are really nice, because when you make this equation in kilowatts, you can say, okay, it's very related with Maria Jose's presentation. If you have this building, this is a real building with its temperature in green, more or less 24 degrees. Outdoor temperature in blue, more or less 5 degrees. This was January 2015 in one building we were monitoring, where we also were measuring in kilowatts the electrical and the heating gains. And we were measuring also more or less the solar gains, this value here. So we were able to measure solar gains, heating and electric heating gains, and electrical and occupancy gains more or less, but obviously we were not able to measure the accumulation term. But if we take this point where indoor plus outdoor divided by 2 was more or less 15 degrees, and after 3 days, indoor plus outdoor, and it was more or less 15 degrees, let's say the thermal level of the building was quite similar between these 2 points. And then we make this mathematical, very ugly thing of making the integral between time 1, where the thermal level and the thermal level were the same. This is time 1, time 2. It's more or less 3 days between these 2 points. And we were, well, we actually we had minutely data average to 10 to 1 hour data, and we have these signals. So the internal energy is actually, if you remember from thermodynamics, this is a property of the system. It's not dependent on the time. It's only dependent if you make this integral. It only depends. Yeah. It only depends on the temperature of all the masses with their specific heat at initial time minus the summatory of each of the mass types. This is mass of the air within the building multiplied by the specific heat by the temperature of the air at the beginning minus the temperature at the end. Mass of the concrete of the building multiplied by the specific heat multiplied its temperature at the beginning minus. It's a very hard summatory to be done. Actually, it's not possible to be done. But we are really happy because you don't see here multiplied by delta T. Yeah, delta T is actually the time between each of the measurements you have here. And this delta T you have here, do you see that this term that is actually, this integral is actually the area below the red line. This integral is actually the area below the orange line. Yeah, and this integral is actually the area below the blue line. But do you see that the longer the delta time is, the longer the period you take, this difference will tend to infinite, these terms will tend to infinite, and the accumulation term will be the same, and it only depends on the initial and the final temperature. And if this term is to infinite, and this is something that it's fixed, only dependent on the initial and the final temperature, the longer the period, the effect of the accumulation term would be smaller, no? When you make this assumption. And the bigger the temperature difference, the smaller the effect of neglecting it. Yeah, actually, neglecting this term leads you to this very simple way of calculating the heat transfer coefficient or the heat loss coefficient. And it's here where, you see, this is what we want to calculate. And here we have all these terms are measurable variables. So all these measurable variables, yeah, are measurable, but they have to be, do you see that this heat loss coefficient, even if the UA value, it's actually doesn't nearly vary, even if you change the thermal level, yeah, its variation is small. The ventilation and infiltration might make variations in this heat loss coefficient, but look at this. What is the uncertainty of this guy here? Actually, here, if you calculate it and if you would be able to measure all this, the uncertainty will tend to 0. But the thing is that many of these things are not measurable. And this is very important. This is a physical model. This is, if I would measure this perfectly, I will get the perfect measurements. So if you have a white box that is very simple and you can see all the variables that you can measure that will give you whatever you want to measure, any other method at least will have the uncertainty related to the measurements that you see in this term. Yeah, and making this assumption of neglecting the accumulation term, here you will have the uncertainty of the heat gains that depend on the measurement devices for measuring the heating, the wattmeters that will measure the electrical gains, The solar gains are very hard to measure and should be as small as possible. And then the tain and T-out, they will have their uncertainties. And do you see that if tain is 20 degrees and T-out is 20 degrees, it's impossible to get a heat loss coefficient. Obviously, in summer, that's why you will get the stupid things when you try to measure it. You need to, the selection of the period is crucial. Actually, we did some trials and we say that the period to be able to properly measure the heat loss coefficient must be cold and cloudy. Cold because tain and T-out would be big. That's really nice, really happy. You will have a very big difference here. And even if you have an uncertainty of 0.5 degrees in 20 degrees, the error is at 2.5%. If you have the same 0.5 degrees of error in a 1 degree difference, the error will be at 50%. So you will never measure proper heat loss coefficient with the small temperature difference. And then heating gains are very easily measurable with calorimeter, electrical gains with wattmeters, and very accurate. And if you take cold and cloudy periods are very common in Europe, even in Bilbao, where we are in Spain, and it's much more sunnier than many countries that you have. And if you take all these type of periods, you could measure it quite accurately. So physical modeling is very interesting because you can, once you have all this done in this physical model, you can put the errors of each of the measurable variables, and you can, let's say, take them, even this term that you neglected, the accumulation term, you can obtain more or less which would be the uncertainty if you transfer this uncertainty to the end of the estimation. We apply that method to this big building, this West Block, and we were able to find in 2 different winters 6 independent periods. It was, for example, December, January, February, March, December, January. I don't remember them. I'm inventing them. Yeah, but it's different periods, completely independent between them. And you see that the HTC, even if in this building we know that the infiltration heat loss coefficient was not constant because it was dependent on the wind velocity. Yeah, even if we had this variability due to that term, the heat loss coefficient calculated in independent periods was very similar in between them. So the conclusions were that at least the uncertainty sources identified in physical modeling will exist in any other gray or black modeling approach. This is, if you are able to do white box modeling, and you know that you will have these errors in the variables you measure, those at least will be in any other type of modeling. And in other modelings, the modeling will also introduce some uncertainties. No? So not all periods are valid for HTC estimation. Cold and cloudy periods will always provide more accurate HTC estimates. Yeah, it's impossible to measure HTC if there is no temperature difference. Yeah, and if there is no heat gain that is being lost through the envelope that you want to model. And the periods with similar indoor to outdoor temperature cannot provide accurate HTC estimate. This is if tain and T-out are similar, you will never get HTC estimates that are correct. And unless thermal capacities are considered in modeling, the periods or subperiods must try to have similar thermal level of the building in the beginning and at the end. This is coheating. It's very interesting. It makes 24 hours average. And why? Because usually buildings has 24-hour repeated behavior. And if you take 7 a.m. to 7 a.m., it will be similar, the thermal level usually in winter. And the periods must be complete without excluding data points, even if indoor to outdoor temperature is small during some data points. Yeah, you cannot exclude data periods in between them. We have all that in this document we prepared some years ago. And thank you very much. Yeah, it was 2 minutes. So.
Thanks, Aitor. We'll take any questions after the session.
Perfect.
Yeah, sure. Okay. Amy?
Okay, so hi everyone. I'm not going to introduce any particular individual thing. I'm kind of going to give you a bit of an overview. First of all, as to what Ireland's interest in heat transfer coefficient measurement or understanding is all about. And I'll go through national priorities in this area, and then I'll talk through one project in particular, and then I'll just signpost to other ones that we have ongoing that might be relevant. So in Ireland, the government basically and the funding agencies haven't been that interested in any projects to do with measuring heat loss physically in buildings, through walls, through ceilings, through whatever else. Most of